Imagine an enterprise environment where 50 specialized AI agents are deployed to handle diverse tasks, from CRM updates to logistics tracking. To function, each agent needs access to 50 different data sources and internal tools. This creates a terrifying end-to-end complexity matrix resulting in 2,500 unique integration points. In professional system architecture, we call this integration hell. Every time an underlying API changes, dozens of agents break simultaneously because they lack a common language. Without a standardized protocol, the maintenance cost grows exponentially, creating a bottleneck that prevents AI from scaling beyond small-scale pilots. This fragmentation isn't just technical debt, it is a systemic risk that leads to hallucinated data and operational paralysis. As architects, we must move beyond these brittle, point-to-point connections if we want to build resilient intelligence systems. Today, I will show you how to escape this trap and transform this chaos into a structured, manageable ecosystem. By the end of this lecture, you will understand the specific technical framework that turns this nightmare into a plug-and-play reality. Think back to the era before USB. Connecting a printer, a mouse, or a scanner required specific ports and proprietary drivers for every single combination of hardware. We are currently in that same dark age for AI agents. Every LLM provider, be it OpenAI, Anthropic, or local models, requires its own specific wrapper or tool calling implementation. If you want to switch your agent's brain from one model to another, you often have to rewrite the entire integration layer because the context is formatted differently for each model. This lack of interoperability is the single biggest barrier to the agentic enterprise. Just as the universal serial bus revolutionized hardware by decoupling the device from the interface, the Model Context Protocol provides a unified layer that allows any agent to talk to any data source without custom glue code. This shift from bespoke integration to standardized protocols is what separates amateur hobbyist projects from professional enterprise architecture. Understanding this shift is critical for anyone designing the next generation of digital labor. Is this standardization really possible for something as complex as human-like reasoning? Let's look at the architectural blueprint we are about to master. To master MCP, we must go beyond simple API calls and understand the full protocol stack. In this course, we will break down the three core pillars: the technical transport layer, the capability negotiation between server and client, and the security boundary for sensitive data. We will analyze the JSON-RPC foundations of MCP and how it manages stateful interactions in a stateless web world. Our objective is to build a technical decision matrix that helps you choose when to use MCP over traditional REST or gRPC, especially when dealing with high-latency LLM responses and complex context requirements. We will also dive into enterprise-grade deployment frameworks, ensuring your agents remain compliant with industry standards for data governance. By the time we finish, you won't just be using MCP, you will be designing robust, scalable integration hubs that can handle hundreds of heterogeneous agents and data sources. This is about building the nervous system of the modern AI-driven organization. But before we touch the code, we must understand where this protocol sits in the long history of system architecture. In the field, we often see new technologies being treated as isolated tools, but the most successful architects recognize them as part of a historical lineage. MCP is not a sudden anomaly. It is the evolutionary successor to the Enterprise Service Bus, ESB, and the API Gateway. In the 2000s, ESB solved the spaghetti problem for legacy systems. In the 2010s, API gateways managed the microservices explosion. Now, in the era of intelligence, MCP addresses the unique challenge of contextual integration where the data isn't just a payload, but the very knowledge the AI uses to reason. As an architect, I view MCP as the final piece of the distributed systems puzzle, providing the governance layer required for autonomous agents to operate safely within a corporate firewall. It represents a fundamental shift from data integration to intelligence integration. This perspective is vital for passing high-level architectural reviews and for ensuring your systems don't become obsolete within a year. To truly appreciate this evolution, we must go back and look at how our ancestors solved the integration crisis in the pre-AI era journey we begin in the next chapter. To understand where we are with MCP, we must look at the lineage of enterprise integration. 20 years ago, we lived in the era of SOA and the Enterprise Service Bus, or ESB. We relied on heavy protocols like SOAP and WSDL, which were powerful but extremely rigid. As we moved into 2010s, the industry shifted toward microservices and the AP gateway pattern, favoring the simplicity of REST and JSON. However, these patterns were designed for human-defined logic and static integration points. In the age of AI agents, we face a new problem. LLMs need to discover and use tools dynamically without us hard-coding every single endpoint. This is why MCP is being hailed as the language server protocol for AI. It represents the shift from manual API orchestration to autonomous context discovery. But wait, if REST worked for a decade, why can't it handle the needs of a modern AI agent? The answer lies in the fundamental architecture of state and context management, which we are about to dissect. In traditional enterprise architecture, REST is king because it is stateless. According to RFC 7231, every request must contain all the information needed to understand it. While this is great for scaling web services, it is a nightmare for LLMs. AI agents require deep context awareness. They need to know the state of the conversation, the schema of the database, and the available tools simultaneously. When we use traditional REST for AI, we end up stuffing massive amounts of metadata into every prompt, leading to context bloat and high token costs. MCP changes the game by standardizing how context is served, moving from stateless data fetching to a stateful understanding of environment capabilities. If we don't fix this mismatch between stateless APIs and stateful AI, our agents will remain expensive and forgetful toys. But how exactly does MCP outperform a well-optimized custom webhook? Let's look at the side-by-side performance metrics and developer experience. As an architect, you might ask, can't I just use custom webhooks? You could, but you'd be building a maintenance trap. Custom webhooks create a tight one-to-one coupling between the model provider and your data. If you switch from OpenAI to Claude or a local Llama instance, you have to rewrite your integration layer every time. MCP introduces a standardized server layer that abstracts the data source. Whether it's a PostgreSQL database, a Slack workspace, or a GitHub repo, the MCP server presents them in a way that any MCP-compliant client can immediately understand. This bidirectional communication ensures that the model isn't just receiving data, but can also query for capabilities. By adopting this standard, you reduce your integration debt by orders of magnitude. But is this just another way for big tech to lock you in? Actually, it's the exact opposite. It's your ultimate escape hatch from vendor lock-in. The most strategic advantage of MCP is the decoupling of the reasoning engine from the context source. In the past, if you built a sophisticated agent for a specific LLM, your business logic was trapped in that ecosystem. MCP breaks this silo. By standardizing the interface, you can swap the brain the model while keeping your sensors and hands the MCP servers intact. This creates a plug-and-play architecture where your enterprise data remains sovereign. We are moving toward a world of multi-agent systems where different models from different vendors must collaborate on the same data. Without a protocol like MCP, this would require a mess of middleware. With MCP, it becomes a clean, radial architecture. This is how we achieve true interoperability in the agentic era. Now that we understand the why, it's time to open the hood. In the next chapter, we will dive deep into the binary and JSON-RPC internals of how MCP actually moves data between the client and server. To truly understand why the Model Context Protocol is revolutionary, we must look at its architectural foundation. MCP is not reinventing the wheel. It is standing on the shoulders of proven enterprise patterns. At its core, MCP utilizes JSON-RPC 2.0 for its message framing, ensuring a lightweight and stateless communication model. But the real flexibility lies in the transport layer. In local environments, it uses Systio standard input and output, which allows for the lowest possible latency between an agent and its host. For remote or distributed scenarios, it leverages HTTP with server-sent events, SSE, providing a persistent downstream for the server to push context to the client. This dual transport strategy solves the last-mile problem of integration that older ESB models struggled with for decades. But why did they choose JSON-RPC over something like gRPC or GraphQL? The answer lies in the simplicity of implementation across various programming environments. But wait, a transport layer is useless if the two parties don't know how to introduce themselves. How does the handshake actually start? The lifecycle of an MCP connection is a rigorous sequence designed to ensure compatibility and security. It begins with the initialize request. Here, the client and server exchange version information and, more importantly, capabilities. This is where the server declares what it can do. Does it offer resources, tools, or prompt templates? Unlike the rigid WSDL files of the SOAP era, this handshake is dynamic and negotiable. Once both parties agree on the protocol version and capabilities, the client sends an initialized notification. Only after this handshake is complete can the actual context exchange begin. In the field, we often see integration failures because developers skip proper capability checking, leading to runtime errors when an agent tries to call a tool the server doesn't actually support. This stateful initialization within a stateless message format is a sophisticated design choice. But once the handshake is done, how does the agent actually distinguish between just reading data and taking action? In the MCP universe, every integration falls into three core primitives. First, we have resources. Think of these as the nouns of your system. They are passive, read-only data sources like log files, database schemas, or API documentation. They provide the grounding for the model. On the other hand, we have tools. These are the verbs. Tools are executable functions that have side effects: writing to a database, triggering a deployment, or sending an email. From an architectural standpoint, the distinction is critical. Resources are idempotent and safe to pull, while tools require explicit permissions and can change the state of the world. In the enterprise, confusing these two leads to disastrous hallucinated actions, where an agent mistakenly treats a dangerous command as simple information. Understanding this boundary is the first step toward building a safe agentic architecture. But wait, if the model has the data and the tools, who tells it how to use them effectively? The third primitive is the prompt template. This is often the most misunderstood part of MCP. In traditional integrations, we just sent raw data and hoped the model knew what to do. MCP prompts allow the server to provide standardized instructions or context recipes. Instead of the client guessing how to interpret a complex resource, the server can provide a predefined prompt template that guides the LLM on how to reason over that specific data. For example, a Jira MCP server might provide a summarized sprint prompt template that automatically structures the raw issue data into a coherent report format. This architectural pattern moves the prompt engineering logic closer to the data source where it belongs. By doing this, we reduce the cognitive load on the primary agent and ensure consistency across different models. What happens when the server needs the model to help it complete a task? This is where the hierarchy of traditional computing is completely flipped. In traditional systems, the client always calls the server. MCP introduces a paradigm shift called sampling. This is essentially inverse control for AI. In a sampling flow, the MCP server can request the client the LM to perform a completion task. Imagine a database server that encounters a complex SQL error. It can sample the LLM to explain the error or suggest a fix, then continue its own execution. This allows for model routing where the server can choose a specific model optimized for a subtask. From an architect's view, this turns the MCP server from a passive data provider into an active orchestrator. This is the secret sauce for autonomous agents that need to solve problems recursively without human intervention at every step. However, this power comes with a significant risk. What if this creates an infinite loop of models calling models? When we combine resources, tools, prompts, and sampling, we arrive at the standard agentic loop. This is the architectural holy grail that we've been chasing since the early days of service-oriented architecture. We now have a standardized way to give an agent eyes, resources, hands, tools, a brain LLM, and a guide prompts. In the field, we refer to this as the context-action reasoning loop. By defining these interactions through a formal protocol, we can finally swap out models or data sources without rewriting the entire agent's logic. This is why MCP is the critical infrastructure for scaling AI in the enterprise. It moves us from brittle, one-off integrations to a robust, interoperable ecosystem. But as we open these deep pipes into our enterprise data, we face a terrifying new reality. How do we stop an agent from accidentally deleting our entire production database? That is why our next chapter on security is the most important one yet. In the enterprise integration landscape, we often focus on the perimeter, but MCP introduces a sophisticated indirect prompt injection vector that bypasses traditional firewalls. When an MCP client fetches data via a read resource call from a compromised external source, that data isn't just text, it's instructions. A malicious payload embedded in a PDF or a database record can hijack the LLM's logic, forcing it to execute call tool with unauthorized parameters, such as deleting a production cloud instance or exfiltrating sensitive RND data. This isn't a theoretical bug. It's a fundamental shift in how we must view input validation. In the MCP era, every piece of data retrieved from a tool must be treated as untrusted code. We are moving from a world of data sanitization to a world of intent verification. Have you considered that your agent's greatest strength, its ability to use tools, is also its most vulnerable backdoor? But wait, the danger deepens when we look at how these injections manifest as traditional architectural failures. To secure MCP, we must map the OWASP top 10 for LLMs directly onto our integration architecture. The most critical risk here is server-side request forgery, SSRFs, disguised as an MCP tool call. Imagine an MCP server that provides a fetch-URL tool. If not properly sandboxed, an agent could be tricked into scanning internal metadata services or accessing private enterprise subnets. We also see privilege escalation where an MCP server runs with root or admin tokens, but the user interacting with the agent should only have read-only access. This mismatch creates a confused deputy problem where the agent acts as an intermediary for unauthorized actions. As architects, we must enforce the principle of least privilege not just at the user level, but at the tool definition level within the MCP manifest. Mapping these threats is step one, but how do we architect a system that is inherently resistant to these leaks from the ground up? Despite these threats, the MCP local-first architecture provides unique security advantage that cloud-only AI plugins cannot match. In a traditional SaaS plugin model, you must expose an HTTP endpoint to the world, creating a permanent attack surface. With MCP, the server typically runs as a local process or within a sidecar, communicating over standard I/O or local pipes. This means your sensitive database schemas, internal API docs, and proprietary code never need to leave your air-gapped environment or VPC. The LM acts as the orchestrator, but the muscle the MCP server operates behind your firewall, governed by local OS permissions. This architectural decision fundamentally mitigates data residency concerns and external eavesdropping. Local execution is a massive win for compliance, but it introduces a new headache. How do we govern these autonomous agents without slowing down the development cycle? To prevent agents from making catastrophic autonomous decisions, we must implement a consent-based execution flow. In a professional MCP implementation, the client doesn't just execute every tool the LLM requests. Instead, we introduce a human-in-the-loop, ITL, gatekeeper. When the LLM issues a call tool for a high-risk operation, like execute SQL or send transaction, the MCP client must pause and present a structured summary to the human supervisor. This isn't just a simple yes/no button. It involves permission delegation where the user grants a scoped session token for a specific action. We call this just-in-time authorization. By designing this flow, we ensure that while the agent is autonomous in its reasoning, it remains subservient in its actions. This balance is the key to scaling AI in regulated industries like finance and healthcare. Consent is our shield, but without a rigorous paper trail, even the best shield won't help you during a post-mortem audit or a compliance check. The final pillar of enterprise MCP security is observability and audit logging. Every JSON-RPC message exchange between the client and server must be immutable, time-stamped, and stored in a centralized telemetry store. An MCP e-auditor component should monitor these logs for anomalous patterns such as an agent suddenly requesting high-frequency tool calls or attempting to access resources outside its typical semantic scope. We use these logs not just for debugging, but for reconstructing the agent's chain of thought during a security incident. If a database record was altered incorrectly, we need to know, was it a hallucination, a prompt injection, or a logic error in the MCP server code? Compliance frameworks like OCC2 require this level of traceability. By capturing the full context including the prompt, the tool arguments, and the server response, we create a transparent system. Security and governance are the foundation, but how do we actually orchestrate multiple secured agents to solve complex business problems? That's where multi-agent design patterns come in, which we will explore next. In the early days of enterprise integration, we faced the spaghetti architecture, nightmare point-to-point connections that became impossible to manage. As we move into the era of AI agents, we risk repeating history. A direct connection model, where one LLM client talks to one MCP server, is simple for a pilot project but fails at scale. In a professional enterprise environment, we must transition toward an MCP gateway or hub topology. This acts as a centralized service registry similar to what we saw in SOA or microservices. By placing a gateway between your diverse agents and your backend MCP servers, you gain a single point of control for tool discovery, logging, and security enforcement. This isn't just about connectivity, it's about making your enterprise tools discoverable by any authorized agent without manual reconfiguration. However, this centralized hub creates a potential bottleneck that every architect must anticipate. This raises a critical question. How do we prevent our centralized gateway from becoming a single point of failure under the massive load of real-time agentic workflows? Architecting for scale in an AI-driven enterprise requires more than just functional connectivity. It demands high availability and load balancing. Unlike standard stateless REST calls, MCP sessions often involve stateful context and persistent JSON-RPC connections. To handle thousands of concurrent agent sessions, we implement a layered stack. At the bottom, distributed MCP server instances are orchestrated via Kubernetes, while a smart load balancer at the top manages traffic. But here is the catch. Because MCP can maintain state during a complex reasoning loop, standard round-robin load balancing might break the agent's context. We need session affinity or a shared context store like Redis to ensure that if an agent is mid-task, its requests continue to hit a server that understands the ongoing state. This architectural pattern ensures that even if one node fails, the swarm of agents continues to function without losing their train of thought. This is the difference between a toy demo and a resilient enterprise backbone. But wait, while scaling the infrastructure is a technical challenge, how do we justify the cost of this complexity compared to traditional methods? Experienced architects know that every new technology carries an adoption tax. When should you use MCP instead of a standard REST API or GraphQL? The decision rests on the complexity VS value matrix. If your agent only needs to fetch a single piece of data once, a simple REST call is sufficient and has lower overhead. However, when you deal with high-complexity scenarios where an agent needs to autonomously browse schemas, execute multiple dependent tools, or require real-time context updates, the ROI of MCP becomes undeniable. MCP reduces the integration friction by providing a standardized way for the LLM to understand the tool's capabilities without custom glue code for every single endpoint. By evaluating the reasoning depth required by your agents, you can strategically decide which parts of your infrastructure deserve an MCP upgrade and which should remain as legacy services. It's a pragmatic approach to digital transformation. Now, once you've identified high-value targets for MCP, the next hurdle is the actual implementation. Do you have to rewrite your entire legacy backend from scratch? The most effective way to modernize is not through a rip and replace strategy, but through legacy wrapping. You likely have decades of logic stored in SOAP services, SQL databases, or internal REST APIs. Instead of rewriting these, we apply the MCP wrapper pattern. This involves creating a thin MCP server layer that acts as a translator. When the LLM client sends a call tool request via JSON-RPC, the MCP wrapper converts this into the specific protocol the legacy system understands, be it SQL query or a gRPC call, and then maps the results back into the standardized MCP resource format. This roadmap allows for incremental migration. You wrap your most critical data first, providing immediate eyes and ears to your AI agents, while keeping the stable backend intact. This pattern transforms your stagnant technical debt into active, agent-ready assets. As we conclude this look at design patterns, we realize that MCP is not just an interface, it's the beginning of a new era of standardized intelligence. But where does this path lead next? In our final chapter, we will look beyond integration and into the future of autonomous standard-driven ecosystems. As we wrap up our journey through the model context protocol, we must look at the macro-level shift in enterprise architecture. For decades, We fought the integration spaghetti first with EAI, then ESB, and eventually RESTful API gateways. But AI agents introduced a new variable, non-deterministic context requirements. If you continue building one-off connectors for every agent, your technical debt will grow exponentially. MCP solves this by providing a unified transport and capability negotiation layer. It is no longer about writing a custom Python script to fetch Jira data. It is about exposing a Jira MCP server that any compliant agent can query instantly. This moves us from integration as a project to integration as a protocol ecosystem. By adopting this now, you are building a future-proof foundation where agents are hot swappable and data access is governed by a standard interface. This is the same evolution we saw from manual hardware configuration to the standardized world of Kubernetes and containers. But who truly controls this standard, and can we trust it for the long term? Let's examine the governance that will protect your investment. The transition of MCP governance to the Linux Foundation marks a pivotal moment in the AI lifecycle. Historically, proprietary standards failed because of vendor lock-in fears. With the Linux Foundation's oversight, MCP is positioned to become the TCP/IP of AI context. Looking toward the 2026-2030 technology stack, we anticipate the emergence of the AI Agent Interoperability Framework, or AAF. In this future, the context mesh will reside alongside the service mesh, providing discovery, authentication, and sampling across heterogeneous model providers and enterprise data silos. For the senior architect, this means the focus shifts from how to connect to how to govern the flow of intelligence. Enterprises that fail to adopt this open standard will find themselves trapped in silos, unable to leverage the rapid advancements of multi-agent orchestration. We have covered the why and the how. Now the question remains, is your organization ready to lead the protocol revolution, or will you be left behind in the era of manual, brittle integration? This concludes our masterclass on the model context protocol. Go forth and build the future of autonomous systems.